All right, so hello everyone and welcome. Thanks for joining us today. My name is Adam Kraut. I'm with BioTeam, and just a quick bit of background. So I've been doing computational biology for around 16 years. In the past 12 years, I've been consulting BioTeam. And so I want to talk a little bit about, data ecosystems and really focusing on the why and the how. Why should we care about data ecosystems and the how? What are some of the sort of capabilities and characteristics that we're seeing in data ecosystems with our clients? All right, so first, who is BioTeam a little bit if you haven't heard of us? So, BioTeam is a scientific computing consulting team. We solve complex problems at the intersection of science, technology, and data. So we're a virtual company. That means we've been doing this remote work thing since about 2002. And we're unique in that we're staffed by scientists from lots of different disciplines who learned, HPC and advanced analytics to actually get their jobs done. So I think an important feature of BioTeam is that we're technology agnostic and vendor independent, right? That means clients can trust us to make recommendations and unbiased decisions. We're also known for pioneering open source products in distributed computing. And really, we like to translate scientific drivers into innovative computing solutions. So we try to connect together strategy and execution. So unlike other IT consulting companies, we actually get our hands dirty and we dive deep, because we're scientists first. And so our process is, to assess, design, build, implement, educate, and support scientific missions of our clients. So, since our mission is, solving these problems at the intersection of science, technology, and data, we're actually seeing most of our clients are struggling with some of the same, central challenges and central problems. We like to say that science is always changing, faster than IT. So what that means is that we need really fast and flexible IT solutions. I call this like the IT agility problem. And to do concurrent engineering in biology and computer science, you sort of end up deploying advanced infrastructure. And advanced infrastructure increases complexity, right? And biology itself is already complex. So our technology should aim to be simple, right, and flexible. So this is kind of the compounding complexity problem that we face all the time. Adam talked about it a lot, but data management at scale is really hard, right? You can't really do anything with big data except try to make it smaller. In our experience, maybe 80% of researchers' time is spent wrangling data and fighting with technology, right? So this is a data management problem, and everybody we see is facing this. Some of the ways that this problem sort of manifests itself is, in sort of data not following FAIR principles, right? You may have heard of this, but our data is not findable. Our data is not accessible. It's not interoperable. It's not reusable. So this is one set of data principles, but I would encourage you to think of what are your data principles and what are the principles that drive your data science team. So what is a data ecosystem, right? This term sort of started at the NIH, but it's not really well defined, and there's a lot of different names for it. So I'd call a data ecosystem the set of infrastructure and services that empowers a community of scientists and engineers. So it's not just a thing or a platform or a product. It's a thing and it's a community, right? And I kind of characterize it by more of its key features and its key capabilities more than just pointing at a single thing, right? It has a lot of these features. So the important features, in my opinion, for a healthy life sciences data ecosystem is data discoverability. So if you have petabytes and petabytes of unstructured data, it's not discoverable, right? And Adam talked about this. It also, looks at this idea of data integrity at the origin. So we'll hear from the next presenters about garbage in, garbage out, and how the integrity of data and how much you can trust your data really plays a huge role in how powerful it can be when you're using it in predictions. Healthy data science also means arriving at common languages and sometimes inventing new languages, and I'll talk about that. We also need robust analytical pipelines, and we need to use infrastructure as code, right, so that we can iterate fast. And I'll talk a bit more about this because I really like these concepts. And we need to get away from sort of big monolithic solutions towards microservices and micro front ends, right? This is a trend we're really seeing pay dividends in data science. And also, at the end of the day, we're running experiments, right? So we need the capability to track experiments, to share workspaces, to kind of keep all that data provenance intact. And then finally, I like this idea of applying a DevOps mindset to machine learning and drug discovery with AI. Because I think some of the principles in DevOps really help us accelerate this whole discovery process. All right, so I think the network is probably the foundation of any data-driven ecosystem. So I would encourage you to sort of consider that foundational layer, right? Look at your science network. and understand the data movement patterns, the access patterns, because that's going to be really important. If a lot of people like to say bring the compute to the data, but you also have to bring data to the compute. You're going to need to be able to do both. So your ability to move data is critical for doing sort of large-scale data science. I mean, in a worst-case scenario, you can actually halt experiments going on in the lab and destroy your potential to discover by having just a poor network design, right? In the best-case scenario, you've got a loss-free high-speed network, right, with data transfer nodes that are optimized to match the capabilities of your science. If you're wondering what that picture on the left is, it's actually a cross-section of an undersea fiber optic network cable. And if you're wondering what that costs, it's about $400 per foot. So network investments are important. Another sort of key idea here is this data discoverability, right? So if the primary goal of a data scientist is to locate data, make sense of it, and evaluate that it's trustworthy, our data has to be discoverable. But data sort of naturally diverges into these silos. And we see these all over the place, and silos become problematic, and they come in different forms. So humans themselves, right, our human nature creates silos. We hoard information, we don't share, right? So humans themselves make silos. That's just human nature. Apps and databases, right, create silos when we use them. Organizations themselves create silos by having different departments, different sites, and operating across geographical regions. So these things create real silos that we have to deal with. So when I think about data discoverability, you have to think search has got to be the first class sort of feature of your data ecosystem. If you can't find data, that's generally our primary objective. And a secondary objective to that is assessing the quality of that data. That's actually even harder to do. So some of the things you need for data discoverability are things like GUIDs, right? Globally unique identifiers. And you also need sort of GUID resolver services and ways of sort of locating objects across your ecosystem. Also think about quality metrics and how you might implement that to sort of assess whether data is trustworthy or quality or not quality, right? Also, this is where you're going to sort of deal with sort of file to object mapping. This is where you need to start moving from unstructured to structured data. You can't really get all the way there with completely unstructured data. So starting to think about how you mix unstructured and structured data together is going to be really key. It's really about just this concept of linked data that's going to drive sort of data interoperability in your ecosystem. So garbage in, garbage out, right? Data integrity at the origin, I think, is a critical idea. Too often we're trying to sort of clean up data after we've already collected all this data, and I think that's just really going to be difficult if you're going to try to accelerate machine learning projects. So one way to deal with this is just data integrity at the origin. So making sure your data store is harmonized, indexed in various databases, discoverable and queryable. This concept of good data hygiene, right? And you want to sort of have the data cleaner upstream so that downstream analysis can be more effective. You don't always have to do this manually, right? This isn't necessarily manual curation. You can automatically infer, partial metadata from existing databases or information silos. And we're seeing a huge increase in sort of graph database approaches and scale-first databases like Redshift and SciDB. And so in the best case scenario, you've got this really high-quality curated data set, right, that you can train your algorithms on and develop better models. So data integrity at the origin, I think, is going to be a key aspect of a healthy data ecosystem. All right, so next we have common languages, right? And this kind of covers a bunch of things. I saw somebody in the chat posted about ontologies. And so, absolutely, cross-functional teams need to speak a common language, right? And this is actually a characteristic of high-performance teams, is that they develop common language very quickly and efficiently. This is really critical to your success. So some of the quick wins in this area involve adopting a data dictionary approach or aligning with a consortia or a set of existing standards, right? Places like the GA4GH, or just even picking a file format to standardize on is important. Sometimes you're going to have to develop your own language, right? So don't be afraid to come up with new domain-specific languages if it fits the task and if it can help you improve the experience and communication of your team. I would also argue that choosing programming languages matters, right? So we have the languages we speak to each other, but I think adopting programming languages with a broad use across different platforms is really important. So if I was making a recommendation, I'd probably stick with Python, Go, or JavaScript just because how ubiquitous they are across platforms, services, and providers. So I also want to talk about how informatics pipelines are really benefiting from advances in software development lifecycle. So, lots of advances have happened with configuration management. It feels like I've been talking about configuration management for like a decade now, but we still see widespread use of things like Ansible playbooks and Chef cookbooks to configure servers. Even more so now, we're seeing Terraform and CloudFormation being critical for provisioning these cloud systems and ML workflows in the cloud. And I would argue that this infrastructure as code concept becomes even more important when you're in a hybrid cloud scenario, because the differences in your core infrastructure components are even bigger and bigger. So you can sort of fill in that gap with infrastructure as code. We also see a sort of uptick in Kubernetes-based tooling in ML. So, things like Helm charts and Kubeflow to sort of run workflows and pipelines across Kubernetes infrastructure. So another trend we're seeing is the shift to serverless architecture. I actually think this is a pretty big deal in computing. So, servers in general are kind of annoying to deal with, right? Even more so if you're trying to focus on just experiments. So serverless is quickly becoming the sort of new default computing paradigm. I would encourage everyone to read this Berkeley paper that came out in 2019, which sort of establishes, serverless as sort of the new normal or the new default for computing. And this is really driven by, I'd say, advances in virtualization. So on the left there, you can see some of the inner workings of the virtual machine manager that AWS Lambda uses, called Firecracker. And it's just a really interesting piece of technology because it's just virtualization to the extreme, right, and isolation to the extreme. So it's very interesting. But serverless brings in a whole new set of challenges. And with that, we have a whole new set of design patterns emerging. So the types of patterns we see in serverless are, new style of data lakes, different sort of robust API techniques, state machines, heavily event-based patterns, security sidecars, and different ways of sort of talking to containerized applications, and then just dealing with things like eventual consistency, right? This is a new paradigm in computing that we're just adjusting to now. The cloud kind of poses the question, like, what would you do if you had 1 million CPUs? And some engineers are saying, well, I would develop millions of tiny databases, or weird, interesting architectures like that I think are challenging our ability to even program these things. So looking at formal specifications, languages like TLA+, and just, I'd also encourage you to read this Formal Foundations of Serverless Computing, because it tries to build up new abstractions on serverless that I think we're going to be using for many, many years to come. So the scientific method is iterative, right? And we need tools to sort of track these machine learning experiments and share workspaces, right? And it has to be about collaboration. So, overwhelmingly, we see Jupyter Notebooks as a primary way people are sharing machine learning code. Jupyter Hub is a very common multi-user notebook server that's popular in a lot of the sort of data common stacks we're seeing. But really the objective is tracking your experimental outcomes, your training performance, parameters, data provenance, access control authorizations, right? You want to track all this stuff. And you can start with just, Google spreadsheets, right? It doesn't have to be anything fancy, but just getting into a mode where you can sort of track experiments, track parameters and training runs, and then share them is going to be really critical. Also, I think this can improve the experience around using GPUs and accelerators if you can sort of package things up into notebooks and workspaces that people don't have to necessarily know a lot of the underlying details. There's also a lot of interesting movement in this space with things like SageMaker and Colab and TensorBoard and ways of sort of viewing your experiments over time. And so I really see a huge opportunity for DevOps to have a big impact in machine learning work going forward. Anytime we can sort of eliminate manual handoffs between teams, or just reduce that cycle time between training a model and deploying it for production, right? That's the acceleration we're after. Reducing the time to results, right? Reducing the time to the next iteration, and automating that end-to-end process. So versioning everything, having integration testing, deploying your data and models and code all together, right? And then being able to update that quickly, right? Think of how Tesla does over-the-air updates of their autopilot software and neural networks, right? If you can update these underlying networks and models easily and automatically, it's very powerful. I also think we should be thinking about the explainability of models, right? And we'll hear more about this in the next talks, but we don't necessarily want black box predictions. An explainable model actually allows us to understand how a decision was made. And I would say that this is critical if we want to understand the fundamental biology and chemistry that's at work. All right, and so I kind of want to finish up with a little bit about human factors and pick on this idea of, the 10x engineer. I think, the 10x engineer is a pitfall. You want to avoid someone who's known as sort of the AI unicorn or rock star stereotype, right? Because great engineers aren't driven by individual output. They're great because they work on amazing teams. And data science is absolutely a team sport. If you want to be successful, you have to build a high-performance team that has great leadership. And I would say data science really requires teams that are more diverse than normal. Diversity is a must. You have to find people with a mixed talent and experience and be really inclusive. I want to see these data science teams engaging clinicians earlier in the process, engage lawyers and ethics folks, right? Be very inclusive. You might be surprised. It's going to take a little more energy at first to sort of get everyone working together, but it will pay off in the long run, I think. The team will always be sort of learning and improving, but you have to be really disciplined with your communications, right? There's going to be a lot of sort of level setting at first, but, check your ego at the door, right? Because the ego is the enemy, and if you work hard and put the team first, I think you're going to have the most success. All right, and with that, I'm going to close out and pass it over to Fernanda to talk much more deeper about machine learning.